Welcome back. We're going to pick up where we left off with airport operations. Airports are complex environments with controlled airspace, runway, taxiway systems, and air traffic control coordination. Operations include takeoffs, landings, ground movements, and airspace sequencing for manned aircraft. Controlled airports, Class B, C, D, require radio communication and air traffic control clearance. Uncontrolled airports, often Class G or E, rely on self-announced procedures and see and avoid principles. SUAS operations near airports under Part 107 are restricted near airports to prevent interference with manned aircraft. Operators must request FAA authorization via LAA and C or drone zone for Class B, C, D, and surface level Class E airspace. You must maintain visual line of sight and stay below 400 feet above ground level. Avoid runways, taxiways, and approach paths, even at uncontrolled airports. Violations can lead to flight disruptions, FAA enforcement, and public safety risk. Under 14 CFR Part 107.41, SUAS operators must obtain air traffic control authorization to fly in Class B, C, D, and surface level Class E airspace. Authorization is typically granted via LAA NC, low altitude authorization and notification capability, automated near real-time approval for pre-vetted zones, drone zone, manual submission for complex or non-standard operations. ATC authorization ensures safe integration of drones into the national airspace system, especially near airports. Note, they used to recommend the Before You Fly app to get authorized, but the one that I use is called Autopilot, spelled Auto P-Y-L-O-T, and it's very quick. A letter of agreement is a formal document between the FAA and an operator or organization that clarifies roles and responsibilities for recurring or complex operations, supplements standard ATC authorization, not a substitute for it. May define coordination procedures, operating methods, or special conditions used when air traffic manager deems it necessary for procedural clarity. SIDA, or Security Identification Display Area, is a restricted zone within an airport. Typically includes flight ramps, air operation areas, cargo facilities, and secured terminals. Access requires a SIDA badge issued after background checks and training. Continuous display of credentials while inside the area. SUAS operators working near or within SIDA zones must coordinate with airport security and may require additional vetting. Air traffic flow and patterns. Airports use standard traffic patterns to organize aircraft movement: upwind, crosswind, downwind, base, and final. Typically flown at 1,000 feet above ground level for light aircraft. Patterns may be left-hand or right-hand, depending on runway orientation and local procedures. Air traffic control manages flow at towered airports. Pilots self-announce at non-towered airports. SUAS operators must understand that SUAS operators must understand these patterns to avoid conflicts, especially during takeoff and landing windows. In this diagram, you can see the patterns here for upwind, crosswind, downwind, base, and final. So when someone's coming in for a final, they will have the right of way of the other aircraft. So if an aircraft comes in, they could be told to go around for several times. So if you are operating near an airport, it's good to know the procedures that they follow for this so that you can avoid collision. Runway numbers are based on the runway's magnetic heading rounded to the nearest 10 degrees with the last digit dropped. Example, a runway aligned at 273 degrees magnetic is labeled runway 27. Each runway has two ends, so the opposite end is labeled with the reciprocal heading. Example, runway 27 on one end is runway 9 on the other. Magnetic variation shifts over time, so runway numbers may be updated periodically to reflect changes in Earth's magnetic field. When airports have parallel runways aligned to the same heading, letters are added to distinguish them: left, center, and right. So you can see an example over here. It says 27 left, 27C, 27 right. And then opposite, it would be 9 right, 9C, and 9 left. Runway markings. Threshold markings are white bars at the runway, show where landing begins. Stopways or blast pads are paved areas beyond the runway for aborted takeoffs marked with chevrons. Closed runways marked with large white or yellow X, not for use. Taxiway markings: a center line, a solid yellow line for taxi guidance. Edge markings define taxiway boundaries, solid or dashed yellow. Hold short lines, 2 solid plus 2 dashed yellow lines, stop before entering a runway. Here's a diagram that shows it better. You have your blast pad there with the yellow chevrons, and your displaced threshold is where you would come in after taxiing to get prepared for your takeoff. Those have the white chevrons. So they consider the beginning of the runway where the threshold bar is. When you are landing an aircraft on the runway, they want you to land after that white line. So you have these markings down the runway. You have your center line, but you also have these other markings. And these are your touchdown zone markings and then your aim point. So every line has a purpose. You may not need to know this for SUAS operations. You might not be operating at the airport at all, but you need to know this to be able to sufficiently know airport procedures. And this is on your test, so the FAA wants us to learn it. So here we are. So here are your sign types, the color schemes, and the purpose. So signs that are mandatory instruction will have a red background with white text. They identify critical areas, such as runway entrance or no entry. Location signs will have black background with yellow text, and they'll be outlined in yellow. They show current position of taxiway A. If it's showing you direction, it will be yellow with black text, and it points to the intersections or intersecting taxiways. Your destination It will be the same in guides, terminals, ramps, or services, and information will be the same. It shows advisories. Runway distance remaining will be black with white letters, indicates thousands of feet left. Here is, we have this in the book, but it's not in color, so I figured I'd put it on the slide here to show actual color. I would think it would be in color, but I'm not sure why they didn't have it in color. So with the right-of-way rules, an aircraft that is in distress has right-of-way above any other aircraft in the sky or anything in the sky besides birds. Below that is balloons. Hot air balloons are harder to control, so they have more right-of-way. Same with gliders. And then skydivers or non-powered parachutes come next. I guess they deem that it's easier to control your flight if you're falling than gliding. Which I guess that makes sense, but if you're in a wingsuit, you're also gliding. Know that when the space shuttle comes in, they have to be very precise because they are gliding. They can't power back up if they miss a point or a marker. So that has to be precise. So that makes sense. Below that is airships like blimps or zeppelins. I don't know if we still put zeppelins in the sky, but I saw a Goodyear blimp just last year. So next is any aircraft that's being towed or refueling in the sky. After that is regular air traffic with planes or rotorcraft, which is helicopters. And then at the bottom of the pole, it's UAV. We have to give right away to everybody else. So converging aircraft is when you have two aircraft that are not quite going, they're not going the same direction and they're going to cross the same paths. The aircraft to the right would have the right of way. If they are coming at each other head on, both aircraft must alter course to the right. If an aircraft is overtaking another one, the one being overtaken has the right of way, and the overtaking aircraft must pass on the right. It's different from the roads where we pass on the left. In the sky, we would pass on the right. Any aircraft that's on final approach to land has the right of way over the others that are in the pattern. So primary in-flight hazards for SUAS operation: collision hazards. With other aircraft, you could very well collide with other aircraft. I mean, you wouldn't think that that happens often, but my first time flying a Cessna, we were flying over, I think, between Clark County and Estill County. Air traffic control mentioned to us that there was a plane underneath us, and we didn't see a plane. And I looked down out my window, and there's a plane less than 1,000 feet away. A bright orange plane, too. And we didn't see it approaching. So it happens. Trees, buildings, towers, power lines, they are all obstacles that you will deal with for sure. You wouldn't think that you do, but or that it's easy to stay clear of these things, but sometimes you don't see the power lines or see some wires. Most helicopter crashes are because of power lines. Also, birds. Colliding with a bird. Some birds will see your drone in the sky and attack it. They don't like it, it disturbs them. So, to avoid collisions, mitigation is maintain visual line of sight, pre-flight airspace vetting, and use geofencing and obstacle avoidance sensors. So loss of control, there's signal interference, cell phone towers and electromagnetic sources, some power lines can interrupt. GPS loss or spoofing can cause flyaways or erratic behavior. Then there's misjudging, pilot error, misjudging altitude, speed, or control inputs. To mitigate this, you would use frequency hopping radios, maintain firmware updates, and conduct pre-flight signal checks. So there's also weather-related hazards. We'll go more into that next week. But wind gust, precipitation, thermals, and turbulence. You don't want to fly your drone in precipitation. It can go bad. It can ruin your drone, and if it's a commercial drone, it's likely going to be pretty pricey, and you don't want to do that. So thermals and turbulence, we will also cover that a little more, but thermals and turbulence, your drone will experience that just like an aircraft will in the sky, and it can take your drone down. So you want to be sure to check your METARs and TAFs and make sure that you know what the weather is going to be like. Battery and power failures, overheating or swelling of the batteries can definitely bring your drone down. A voltage drop or improper charging or storage. Use battery locks, pre-flight voltage checks, and temperature monitoring to make sure that your batteries are good. So, industrial production facilities. The hazards there is RF interference from machinery, wireless networks, and control systems. Magnetic fields from motors, transformers, or welding equipment. And thermal plumes and air turbulence from exhaust stacks or HVAC systems. Restricted airspace or facility-specific flight bans. Mitigation. You can conduct site surveys for RF and magnetic interference. Use manual flight modes when GPS or compass reliability is compromised. And coordinate with facility safety officers and check NOTAMs or LOAs. So back to the precipitation. P static is precipitation static, and it is the buildup of electrical charge on an aircraft due to friction with atmospheric particles like rain, snow, or dust. Can cause radio interference, GPS degradation, and erratic control signals. So you can lose your telemetry and where you're controlling, navigation drift or flyway risk, and sensor anomalies, compass errors, barometer spikes. Use shielded wiring, EMI resistant components, and grounding techniques. Avoid flight in high static environments or heavy rain. So that is it for the National Airspace videos. I will see you next time, and we will be on chapter 3 with weather.